Welcome to week 10 of this course on big data. Uh, here, we will actually focus on a specific branch of machine learning that's called as deep learning and how it executes against large scale data sets in the cloud. So, this is actually the last week of lectures as part of this course. So, this kind of culminates um, into a uh, into one of the more practical aspects of data science done at large scale, which is taking a deep learning model and applying it on streaming data. So that'll be the last of the examples that we'll see today. And instead of an assignment, we will actually have uh, the final programming test itself, which will actually look to test you on a very similar example to what we see. Okay, so let's get further into this week's lectures. Before we get started on what makes deep learning on big data challenging, let's actually just spend a bit of time talking about what deep learning itself is. Some of you might have had the chance to do the deep learning course, you might have elected for it, whereas some of you might not have chosen this path, you could have chosen another path to come to this course. So let me give a primer. I won't be going into details of deep learning as part of this particular week's lectures. So encourage you to read up appropriate materials online. There is enough and more that's available. So what is deep learning? First and foremost, it is not a different algorithm. It is not a different type of machine learning. It's in fact a technique in machine learning. Machine learning is much broader. That works very well on pattern mining style problem statements. And the way it works is by having a lot of um, you know nodes in the neural network. So specifically, it's actually a way of architecting the neural network, both in terms of number of nodes in the network as well as the number of layers of these nodes in such a way that the ability to recognize patterns is something that such a vast number of nodes and a great number of layers of these vast number of nodes are able to achieve. But it's not just that it's able to recognize patterns, but also it's able to play it back. So it's able to regurgitate the patterns, and at levels of accuracies which are far higher than what was previously possible with conventional machine learning techniques. And in fact, of late, in the last, I would say, 8 to 10 years, the extent to which such algorithms have outperformed humans is quite astounding. I mean, assuming an average human cognition level. So, examples of this are, for instance, the ability to look at an image and say what it is, the ability to reproduce design by looking at a collection of images and generalizing from there, the ability to read text and understand what the patterns are, to be able to summarize vast bodies of textual data into succinct summaries which are very easy to understand, etc., etc. So there's so many applications, so many ways in which such architectures have been proven to be better than most humans in terms of their ability to recognize patterns and play it back. The challenge with such algorithms, so it's both a feature and a challenge, is that because there are so many layers of these very vast number of nodes in that neural network, that in order to truly train them and create the mechanisms that it stores, recognizes and stores the patterns in some shape and form, and is able to play it back, requires massive data sets. And I'm talking about not just raw data, but actually labeled data, potentially running into billions. There are techniques to work around this. Like, for instance, there is actually a technique that's called as transfer learning, which is taking an existing deep learning network, um, removing the outer layers and then have it be trained for a different objective, which is related in the sense of needing and requiring the same data or working on patterns which are similar. So in that kind of a setup, the rest of the network layers and the nodes and the weights that interconnect the nodes, they continue to be applicable. It's just that the final layer, which is responsible for determining the answer for a specific pattern matching problem, that changes based on the new problem statement that you're looking at. So you don't have to have that millions of labeled data points because you don't have to train the entire network. You just have to train the interconnections between the last part one and the last layer. So that kind of transfer learning doesn't require that much amount of data, but that's more the exception than the norm. A typical deep learning problem statement requires massive data. The other thing that it requires loads and loads of is compute power. So it turns out that for the most part, the fundamental unit of computation when deep learning executes is what is called as error propagation, error related adjustments to the weights that interconnects the nodes, right? So that operation is fundamentally a matrix multiplication, matrix math essentially. So to be able to do that at large scale, turns out that the set of devices or set of chipsets that were invented for gaming and video processing back in the day are now proving extremely capable and adept at doing such matrix math, right, that's required for deep learning to go much, much faster than conventional CPUs that you see in a laptop. So such devices are called GPUs, or graphical processing units. The name originates from gaming and video industries. But then off late, if you see, the world of GPUs is completely shifted towards primarily servicing AI-driven workloads. Okay, so most of what you see as the power of AI nowadays, like ChatGPT and DALL-E, Stable Diffusion, Midjourney, all of those are fundamentally deep learning architectures, and that's why there's a lot of interest in learning about how deep learning works, etc. One interesting thing about deep learning is there has been no formal academic proof that outlines why deep learning networks perform so well on computer vision problem statements or pattern recognition problem statements compared to, let's say, previous approaches to machine learning. So just to contrast that with a bit more color, conventional machine learning techniques require you to do feature engineering, require you to select a model, hyperparameterize the model, and then finally deploy the model. So in a pattern matching problem statement, let's say for instance, I want to be able to take a photo of me at this stage, right? Me looking into this camera, and I want to take these kinds of photographs across all the professors as part of this degree, and have a program that automatically recognizes who the person in the camera is and assigns the correct name, right? So in my case, it should look at the photo and then say this is Rangarajan, right? So the ability to do that in a classical machine learning sense is actually much harder. Why? Because you have to hand engineer the features. So for instance, my face is characterized by certain things, right? You have to model all those features, and those features might look quite different for somebody else with some other face. Right? Somebody else might wear glasses, might have a mustache, might have hair, right? Somebody else might be dressed up formally, might be fairer, might have longer ears, right? Might have eyes which are asymmetrical. I mean, so many different variations are possible. Might be a woman, right? Might be having headgear. There are so many different variations. So to be able to characterize all those features in a classical machine learning sense is going to take an enormous amount of domain experience, firstly, Secondly, it takes an enormous amount of trial and error, right? So you take up 10 attributes, like 10 features, like I was mentioning just now. You go train a model, a classical machine learning model, let's say subgroup vector machine or a decision tree, and then come back and try to score the model, basically validate the model. You might find that it's actually not doing very well on certain phases, right? Like for instance, people dressed in informals as an example. So then you go back and add people dressed in informals as one feature, right? How do you guess somebody's dressed in informals? You look at the t-shirt, whether it's collared or not, etc. So what happens then is like a lot of trial and error, and in many cases you pretty much hit the limit in terms of significant improvements that you can make to the model accuracy within like 2 or 3 iterations, and after that you're just clutching for straws. Effectively, you're just making very small increments, if at all, and it becomes like a very frustrating exercise. Whereas for a human, you intuitively look at 2 faces and you say, yeah, okay, this is that person, this is that person, right? It's very easy. So how do you translate that ease of recognition to algorithm is what deep learning really did very well. Okay, so the fundamental deep learning architecture is very conducive for multi-core execution. So it's what's called as task parallelism. So it can take, let's say, specific aspects of the way it updates and dedicate that to a GPU. So that way, if you have multiple GPUs running available in your machine, the entire deep learning weight training can happen super fast. In fact, each such iteration of weight training is called an epoch. So the epoch runs much faster because you have access to multiple GPUs. So that's the context of deep learning. Just a couple of more words on this, especially as it pertains to big data, and then we will look into specific challenges and how we are overcoming them. So the good part about deep learning is that there are enough and more efforts taken by both academia as well as the companies that you popularly associate with AI, like Google, Microsoft, Facebook, etc., who are all making efforts to make deep learning accessible for everybody, like the innovations in AI accessible to everybody. Fast AI is one such example. OpenAI is another example, right? So what they're doing is they recognize the fact that not everybody has access to massive amounts of label data, and not everybody can afford clusters of GPUs. In fact, very few people can. GPUs can get quite expensive very quickly. So what they do is, using the powers of venture capital funding, access to proprietary data sets that others might find difficult to get, as well as the academic horsepower, meaning the brains behind some of the most up-to-date and cutting-edge deep learning research are employed with some of these companies. So what they've done is they've taken all of that and invested in creating pre-trained models. So these are models which have been trained on massive data with GPUs, and the model gets produced as a single packaged file, right? And that model has all the weights ready, which means the weights have been already trained and tested against massive data. And the model has a specific way of execution with the documentation attached to it. The model is also open source in many cases, in most cases, in fact. So you can go peel the layers of the network, so to speak, and understand what is happening where. And you can just use them, right? You can use them in your setting. So as an example, I think ChatGPT was trained on billions of, ChatGPT itself has billions of parameters or billions of weights, but it was trained on pretty much the entire corpus of the knowledge of the world, right? Pretty much the entire World Wide Web, which is accessible as of 2022 or 2021, I believe. That's as of this recording. Obviously, it's going to get updated even further. But the essence is that it's been trained on massive, truly world scale data, right? And it's been trained and ready, and now it's accessible as an API, which instantaneously gives us responses, right, within 5 seconds, within 10 seconds. So that's phenomenal in terms of the access to innovation that's possible. There's varying levels of compression that's possible with a model. Obviously, like a ChatGPT model, which is fundamentally powered by what's called as a GPT. A GPT is a very specific class of algorithms which are essentially what's called as large language models. So GPT-3 is the version that's currently in vogue, but GPT-3 has billions of parameters. So to truly take GPT-3 and run it in your own system means that you need to have like gigabytes of memory to just be able to read the model and store it in memory and use it for scoring. Not everybody has access to that either, right? Like for instance, your mobile device does not have access to gigabytes of memory that's available for a single model to be deployed. So instead, what's possible, and this is also pretty cool, research that's happened, is that you can eliminate certain weights, you can eliminate certain layers in that deep network. You can still preserve the overall functionalities of what it's trying to achieve, but by eliminating the weights, eliminating certain layers, you're reducing the size of the network significantly. But in return, you might also lose some accuracy. So it's a trade-off associated with it. That's a trade-off that you could make knowing your constraints. Like for instance, one of the most earliest examples of an AI deep learning network for computer vision meaning image recognition, was this model called ResNet. ResNet 15 was one of the algorithms that I remember using myself. But ResNet is pretty large in size compared to a typical mobile phone. So there is a mobile-friendly version of it, which is called MobileNet. And that's what we will see as an example later in today's class. So MobileNet is significantly compressed in terms of size. Right? You don't have to spend as much memory as you would spend with ResNet. And it's also faster. But obviously, it's got lesser accuracy. Likewise, there's VGG13, AlexNet, so many of the options. You could take a look at all those available as part of PyTorch in this link. Likewise, other deep learning frameworks like TensorFlow, like MXNet, all of them have their own versions or variants. Okay, so let's take a look at now the challenges of deep learning on big data. So far, we've just given a very, very high-level primer of deep learning. When it comes to big data, naturally the data sets are large, and in this context, I'm talking about data sets which are so large that it doesn't fit into a single machine, not into a single machine that's accessible to you, right? Remember, we spoke about examples of deep learning networks just before, where the data sets are massive. In those cases, the respective companies have access to resources which make all of the GPUs in a single machine at the disposal of a deep learning training process. So they can afford that. But you or I might not be able to afford it. In fact, we might have to make do with clusters of GPUs or clusters of Spark as an example. So what can we do then? Right? So then it's no longer task parallelism. You have to think in terms of data parallelism, divide and conquer, right? What we've been speaking about in this course all these weeks. So how do you then train a deep learning network which has constantly the need to change weights, right? Using the error associated with predicting a class versus what the actual class is. How do you train such a network on top of a data parallel formulation to the problem statement? So fundamentally, does the DL architecture itself get partitioned, which makes it super complicated? Or how do you deal with weight updates? Right? That's a big challenge. So this is one major challenge that needs to be solved when you think about deep learning on really large data. The second thing is, you could think about it as, let's actually solve it using Spark, right? Spark has this construct of driver program and executors running on the worker nodes. We've seen this before. But if you just try to solve this naively using Spark, you could run into a typical problem that will occur then, which is the GPUs become underutilized. Multiple reasons why. So one reason is that fundamentally Spark as a construct is restricted to doing a particular stage of activity completely before moving on to the next stage, and that stage of activity could have skew. Like when it has skew, then some executors work more than some of the other executors, in which case the GPUs in the other executors are running idle. while this laggard takes its own time to execute. Right, that's one problem. The second problem is that a typical deep learning training cycle involves iterations of running these, training on the data and then visualizing the output. Like for instance, if you use Keras or something like that, you might use TensorBoard as a way to visualize the output of the deep learning network, and then you can go use that to make some adjustments. So typically the TensorBoard would run on a driver program. It wouldn't run that on the worker directly. So the iteration cycle, which involves taking the large data sets in the executors and doing rapid iterations on that, and then bringing the results to the TensorBoard in the driver program, and then spending time visualizing that and understanding it, means that the driver program is busy serving you the TensorBoard output, but the worker nodes from the executors at that time are completely underutilized. So in general, the GPU utilization becomes a problem when you just try to naively implement this using Spark. The third challenge that's actually there is that Spark fundamentally is a JVM process, or it's a Java virtual machine based backend. So the data frame that Spark exposes as a fundamental data construct is meant for optimizations that it does on the JVM, whereas a typical deep learning framework is written in Python, and it's also written in such a way that it assumes that the data is formatted in a certain way that's conducive for the deep learning framework, right? The assumptions that it makes. Like for instance, if you use TensorFlow, Keras, etc., you might find yourself creating specific formats of the data, like Parquet or TF records. TF records is, I think, custom to TensorFlow, and that format is very different from the data frame format. So how do you exchange data between the two? It's not as simple as just trying to run a converter, which is doing the conversion in memory, because when you do that, the data sets are large, remember, and Python really performs poorly in doing such an activity. In fact, the hidden complication here is something called as GIL, or Global Interpreter Lock, which Python actually suffers from as a design when it comes to multi-threaded executions. So in executing a deep learning code with Spark, you're moving from a JVM, which is Spark, which is as Spark is running, to a Python process. When you go to a Python process, in the Python process, everything is actually gated by the GIL, and in that handoff, you would find that if you're converting large amounts of data, then that process actually becomes extremely bottlenecked on this. So that becomes a challenge. Then the last of the interesting challenges here is that once you train your data, train your deep learning algorithm, let's say you make it available for scoring. So in the big data streaming sense, you have lots of fast moving data. How do you get the deep learning model available for scoring on this fast moving data is actually a challenge, because most of these streaming frameworks are operating in a way that's completely decoupled in a divide and conquer manner, right? Like we saw Spark Streaming, Dataflow as examples. But when the deep learning network itself runs, the deep learning model is very large in memory, right? So for each of the divide and conquer instance that is running, the assumption that the streaming framework makes is that every invocation is completely standalone and independent of every other invocation, right? That's what massively parallel processing means. So in which case it would assume, or it could get the Python program to load the deep learning network afresh for every invocation of the scoring, right? Which makes it extremely prohibitive in terms of cost, in terms of latency. So that's a big challenge as well. So we've got to solve for all of this, and then we could truly make deep learning model training as well as model scoring applicable on massive data. So we'll take a look at what tools and techniques are available for this in the coming videos. Thanks.